choice was him. We shared many conferences. In particular, we shared one where I was his audience and he was my audience. Like, we were alone in the conference. That was it. And I truly enjoyed a lot his talks, and I guess you will as well, I hope. So, big round of applause for Andrea Leopardi.
Yeah, this is a true story. I was like, Brujo is, I think, the only person in the world that has seen my talk. Just him. You know, I did a talk for him personally, just for Brujo. Let's do this. Ready? Haha, perfect. You kind of raised your hand. Nice. Okay. All right, so let's talk about Beam architecture. This talk is not Elixir specific, so if you write Erlang, it's going to be the same. That's my handle on the internet. My name is Andrea, and I am a member of the Elixir core team. I've been since 2016, so 3 years. I've been working in Elixir since 2014, more or less, and now we're at a point where Elixir is not that young anymore. You can tell by Hacker News that says, like, would you still pick Elixir in 2019? So I think we made it as a language. I work at a company called Community, based in LA. We do messaging stuff. We hire remotely as well. So if you want to give me, just poke me after if you want to know more. I come from Italy. And the best thing that I want to share with you, something about Italy, is I think the best thing that we have in Italy is Italian people that are mad at food that is cooked in other countries and named Italian food, right? There's this account on Twitter called Italian Comments. It just posts screenshots of Italian people that are angry at food, right? I'll show you a few. Obviously, there is no spinach chicken pasta recipe in Italy. In Italy, a recipe like that is a crime worse than a murder. This is very drastic. A world war won't be enough to forget this. They're very geared towards American people especially, so don't feel particularly offended. But very common recipe used in Italy to cause what we call cono del potere, translation, cone of the power, that is a huge and uncontrolled vomit explosion. Perfect. We're just here to watch you burn one chicken parmesan, 4 cheese mozzarella taco pasta alfredo at a time. It's beautiful. Is it hangover meals in it to vomit the last crap out? Very nice. This is like defeated. I really don't understand why you do this. Just like, defeated. Positive impression. So happy that there is an ocean between us, guys. It's very nice. My personal favorite, we're not just offended, we're actually vomiting. Perfect. Lots of vomit talk. Yes, this is the best thing that we have in Italy, is Italian people that are mad at food. And we have a lot. Like, this is not a parody account. This is just people that write this stuff. Anyways, let's talk about Erlang and Elixir. We're going to talk about 2 perspectives. The node perspective, so how to, like, tips and tricks to architect your Elixir application inside one node. So processes and supervision and all that stuff. And then we're going to move to talking about how to architect your application on multiple nodes. So how to the patterns and the tips and tricks again for multiple nodes to work together, multiple Erlang and Elixir nodes to work together. So let's start with a single node. And in a single node, the smallest unit of life and unit of work that we have in Elixir and Erlang is the process. And the process is specifically a unit of isolation and concurrency. So the first tip is use the processes for those things, for isolating stuff and for making stuff parallel. Processes are not a tool to separate logic or to separate code or to separate responsibilities unless those involve isolating stuff and making stuff concurrent, right? So super quick example, say we have a TCP acceptor that's just a process that is accepting TCP connections, and then when it gets the connections, it spawns another process that handles that specific connection. This is a very good use case for processes, right? Because every connection works in parallel, because it talks to different peers over the network, and the acceptor wants to accept connections in parallel. It does it like while the connections are working. And isolation is really important too, because, for example, if a connection goes down, we really don't want the other connections to be affected. They're isolated in the real world, so we want them to be isolated and concurrent in Erlang and Elixir, right? If instead, so this is a good use case for processes because it's like you need isolation and you need concurrency. For a case where you have, for example, a data structure, right? So say that you have a connection, you have this connection process, and then you want to have a session for that connection. That session, maybe it's just a data structure, but maybe you want to put it in a process because it's separated and it's like the logic is separated and it's isolated. It doesn't really work like that, right? The session is just a piece of data structure that belongs to the specific connection. So in that case, what you want to do is just put stuff, put it as a data structure in the connection. And the unit of separation and isolation that you want there is probably a module. So you maybe want to put the code in another module so that it's logically separated, but in the life of the program, it's living inside the process. So that's the first tip. When we're talking about processes, especially when we're introducing processes in the Erlang virtual machine, I keep scratching here because I was bitten by so many mosquitoes during my week in Colombia. I'm just like a full mosquito bite from head to toe. So I'm sorry, I just keep doing like this because it's killing me. It's just killing me. Anyways, when we talk about processes in Elixir, we talk about spawning processes. My advice is never spawn processes. Like if you see spawn, say, oh, no, like I need to figure out a way to do this without spawn. Spawn is like nice, it's very low level, but usually you need to build a robust program, you need a bunch of stuff around spawning that there are better abstractions for, right? So for example, these are a bunch of abstractions that you can use instead of spawning processes manually, right? So if you need a long-lived process with state, you can have a gen server. If you need the same thing but with different states, like a state machine, you have something like gen state machine. Those all abstract spawning away. You'll never spawn, like use spawn on a gen server, right? You have spawn start link, gen server start link, sorry, gen server.start. You have all the stuff. The tools that are provided and set you up with a bunch of nice things that make things more robust, like monitors and all that kind of stuff. Tasks especially are my favorite because usually people are good at telling when to use a gen server and when to use a gen state machine or when to use one of those abstractions, but they're not very good at telling when to use a task, and they often reach for spawn in my experience, right? Because you need maybe to do just something in parallel, or to like spawn off a process to do something and then check on the results, and what you usually do is spawn it and send the message back to the parent and then wait for that message. Those work, but task is the right abstraction to use in those cases because it abstracts a bunch of pitfalls away from you, right? And I want to show 3 use cases for tasks that are super, super like. First one is doing an asynchronous operation. So you just do something, then do something else, and then fetch the result of the first thing. And I will show you then parallel mapping and parallel processing, and then time-boxed operations. So do this for 15 seconds and otherwise just shut down because it's too late. The first one is async operations. The code is pretty straightforward. You just spawn a task with task async and you pass a function. The return data structure task is just a struct in Elixir, and it contains a bunch of information like the PID of the process that you spawned, the monitor, that's the monitor reference for the monitor that's monitoring that process, and it can be used later to fetch the result, right? So here we're doing task async, and we're doing an HTTP request in the function that we pass. The HTTP request is going to start, and then we move to doing other stuff. And then when we're done doing other stuff and we want to fetch the result of the HTTP request, we will do task await. So we pass the task, we do task await, and this is going to block until the task is done, or if the task was done already, it's going to fetch the result right away, right? And this is a super nice pattern. And if you do this with spawn, you have to do monitors, you have to do receive, you have to do a bunch of stuff that you have to create a reference and everything. So this is like a nice abstraction to not have to write that code. Another thing that I super like in tasks is task async stream to do parallel mapping and parallel computation. So it looks like this. The code is pretty simple. The first thing, let's ignore for now, is just a bunch of options, but the bulk of the code is this. Say you have a list of URLs that you want to fetch. You can use task async stream, and you pass a function, and what task async stream is going to do is going to have a bounded pool of processes, let's call it, where each process is going to process one element of the list that you gave it, of the enumerable that you gave to it, right? So in this case, you can see the options, max concurrency 20. This means that it will spawn at most 20 processes, and it will start consuming the first 20 URLs from the list. And it fetches the result, and then as soon as one of them is done, it starts a process for the next one, right? So it keeps a window basically of 20 processes, and this is like, if you try to do this with spawn, you will end up like 99% of the time that I've seen this implemented manually, it's unbounded. So if you have a list of 1 million URLs, you will spawn 1 million processes, which is pointless because you will run out of other resources, right? Like TCP connections. So this is a super nice thing. There's a bunch of fancy options. One that I like is on timeout kill task. This means that you can give a timeout to each task. By default is I think 5 seconds. And if it doesn't finish, it's just killed, and an error is returned for that specific element. So you can just fetch the ones, it doesn't crash or anything. And this is super useful to both do parallel mapping and also parallel computation of something. Like instead of doing a new map, if at the end you do something like stream.run, it will just execute the functions in parallel. So it's a very nice, it's like poor man's flow. So flow is same concept, but if you know what flow is based on gen stage, it's the same concept, but this is much easier to use when you only need these features, right? And then the last thing that I really like is, it's just a bunch of code, but we're going to go through it really quickly, is doing a time box task. Time box task means I spawn a task, and then I want to just give it a bunch of time to finish. And if it doesn't finish during that time, I don't care about what it, like I just stop. If you want to do this with processes, it's a lot of edge cases because you need to stop it, but you need to check that if it sent a response while it was being stopped. It's a lot of monitoring and receives. And with task, it's pretty straightforward. So if we look at the code, we have the task async call, same as before, and then we have this chunk of code where we basically use a trick, which is task.yield, that's the first function that we're calling, that is saying, wait for 5,000 milliseconds, so wait for 5 seconds if the task gives a response, and if it doesn't give a response in those 5 seconds, return nil. And that's why we use OR, so we're saying if a response is not returned in 5 seconds, then call task shutdown, and task shutdown is going to take care of actually shutting down the process, but then if a response comes while it's shutting down, it's going to be returned. So it's going to take care of a bunch of stuff, and we can handle all of those in parallel. So we're saying the semantics of these are if the task finishes in 5 seconds, get the result. Otherwise, shut it down and still get the result if it's there. And if it's nil, it means that it just timed out that we shut it down. If it crashed for some reason, we're going to get exit, and otherwise we get the response. This is a very powerful pattern because it's really concise piece of code, but it's doing something that's really complex, like it's time boxing a task and properly shutting down without leaking messages and without having race conditions on shutting the task down. So it's really nice. All this talk about leaking messages and about having to monitor processes and about just generally sending messages and everything always makes me think of the most important thing that I think that you need to think about, and that's one of the biggest advantages of Elixir or Erlang systems, is that the stuff that you need to be concerned about in an Erlang system inside a node and between processes is a subset of the stuff that you need to be concerned about when you're writing distributed systems, right? So this is how I think of it. Like this is a graph of the stuff to be concerned about, and the inside is process-to-process communication. And then you have a little bit more stuff if you're doing node-to-node communication, but the concerns are very, very similar. So the idea is that the process-to-process, you still have asynchronous communication, which is what happens when you have distributed systems. You have asynchronous communication and you have crashes, right? So you have to take care of two things that also happen in distributed systems. Then we're going to talk about why, like what are the concerns that are just for node-to-node communication, but like the reasoning like this is really nice. And I think that like asynchronous communication and crashes are something that make you write better programs because you have to think about this stuff. And like the language is not trying to hide that the world is asynchronous and that some things crash and everything. So you want to be able to handle those and you want to be able to just deal with those events, right? And Erlang and Elixir force you to deal with that, but in my experience, that results in much, much safer systems, right? And much more reliable systems to write. For example, I like this quote about from Chris Kithley that says, any of your processes will crash at any given moment and all of their state will be lost. So this is a very pessimistic view of how to write Erlang and Elixir systems, but thinking like this is going to force you to write programs that are very reliable, right? Very reliable, because you're basically always concerned that everything is going to burn, which is what actually happens, you know, like actually computers shut down just randomly. So, so for example, what you want to do if you have a process that holds state is you don't want to just keep the state there and like hope that it doesn't crash. You want to have techniques or safety measures so that you don't lose the state. For example, you can flush the state periodically somewhere to a persistent data store. You can make the state rebuildable, so you can use basically the process as a cache for some state that you have persisted somewhere else. Generally, just keep it in mind. That's my best advice. Just keep in mind that this stuff happens, right? And you have to deal with all of that. A bit of advice that I have around processes and message passing is to pay attention to the mailbox. So when you're writing Elixir programs, this bites a lot of people to have leaking messages. So, and this happens usually when you do something like this, where you have a receive, for example, and you're pattern matching on specific stuff. If you get a message there that doesn't match one of the two clauses, it's just going to sit in the process mailbox until it's consumed. If you never consumed it, that's a memory leak. Right? So my advice is to always consume all possible processes, and this is what Gen server, by the way, forces you to do, because if you have a Gen server, you have to define handle info, and handle info you have to define all the possible clauses, because if you don't define the third clause here, where you match on any message, it's just going to crash, right? So you have to define it, or crash, or at least like notify you that this happened, right? This is just silently sitting in the mailbox. So it's nice to be able to always consume all possible messages. So we've talked about processes a little bit. Now let's talk about supervision trees, which is the next big thing. It's like the abstraction that comes next after processes is how to organize processes and how to supervise processes, right, in supervision trees. The idea behind supervision is pretty straightforward. It's basically, have you tried turning it off and on again? As it turns out, this is really effective. If you have a problem with your computer, like my friends ask me, like my phone isn't working, my computer isn't working, I always like really the first thing is just restart it, right? And 99% of the time it works. The principle is the same with supervision trees. So if you get to a point where your process crashes for some reason, because of an unforeseen thing, or because of maybe bad data coming from the outside of your system, then the process crashes. A really smart thing to do is just restart it from a known state, because there's a chance, and usually it's like a high chance, that bug is not going to reappear for a while, right? So you want to be notified of that, but you don't want your system to go down. And it's usually the system heals itself up until maybe that weird case happens again, right? But at least you're covered until that happens. So it's a really effective strategy, and it usually really works. So let's talk about a bunch of tips to work with supervisor. The first one that I'd like to give is to really design your supervisors on like a piece of paper. It's really hard to visualize supervisors when they're written out in code, and Observer is a little bit better, but it's still not the best to visualize stuff. I really like to draw my supervisors, and Usually, you want to draw like the components of your system. You're going to want to draw the like external components, the internal subsystems in your system, basically, and you want to design your supervisor based on that. And doing that on paper usually like makes the design much easier to understand and much better. The next step is to really know the strategies for supervisors. So we have one for all, and rest for one. Those are the main ones. Well, those are all the ones that we have. One for one means that if you have a supervisor with multiple children, if one child dies, then the supervisor only restarts that child. One for all means that if a child dies, the supervisor restarts all the children. And rest for one is a weird one, but it means that if a child dies, all the children that are after it are restarted, but not the children that are before it. So those are really important, and they all have their use cases, but it's important to understand the strategies for supervision trees. And this goes hand in hand with the next step, which is to really nest your supervision trees, like make your supervision trees nested. And let's see an example of that, because I think it's one of the best advices that was given to me is to nest supervision trees, and I've been doing it since, and it works very well, I think. Let's see an example. Let's say we have a supervisor, soup on top, and then we have a state process that contains some state, and then we have a bunch of workers. And the workers need the state to work, right? They talk to the state process in order to work. If a worker goes down, the state isn't affected because the state is just holding some state, right? But if the state goes down, if the state process crashes, the workers need to crash somehow, right? Because we don't want, because they can't work without the state. So let's try a bunch of strategies for this. Let's just put everything under one supervision tree, one supervisor. So it's a flat supervision tree, and let's go through the strategies that we have, right? So the first one is one for one. What happens if a worker dies with one for one? That's exactly what we want, right? If a worker dies, then it's just restarted, and the state isn't affected, right? But what if the state crashes? If the state crashes, the state is restarted, but while the state crashed and is restarted, the workers can't work properly, right? The workers will fail because they can't access the state. So this is not the strategy that we want. What about one for all? This means that if a worker dies, everything dies, right? And this is not what we want either, because if a worker dies, the state shouldn't care. The other workers can work with the state, right? It's good, this strategy, if the state crashes, because if the state crashes, we crash everything and we restart everything state and then the workers, so it works. But if a worker crashes, it's not really our thing, right? Let's try rest for one. In rest for one, if the state crashes, it's the correct behavior, because everything else after the state is restarted in the supervision tree. But what happens if a worker dies? We just have to be lucky, right? Because if, for example, if the middle worker dies, then the next worker is restarted, so part of the workers are restarted, but it's not really like strategy that makes sense, right? Like if the workers are the same, then it shouldn't matter which worker dies. And here it matters, because if the first worker that was started dies, then all of them die. If the last one dies, then only that one is restarted, right? So there's no strategy that works for this supervision tree for the semantics that we want, which is if the state crashes, we restart everything. If a worker crashes, we just restart the worker. So what we do here is, what we can do is nest supervision tree, so make it more nested. And we do that by introducing another supervisor. So in this case, we introduce a worker supervisor, that's W_sup, that's a worker supervisor. And now we have the state on one side, and then we have a nested supervision tree on the right, where we have the workers under the supervision tree. Now we can devise strategies that they're gonna work exactly like we want. So we can have the worker supervisor be a one-for-one supervisor, so that if a worker crashes, it's isolated under the worker supervisor, and it's restarted by the worker supervisor. Only that worker is restarted. The main supervisor can be a rest for one, because if the state goes down, then it's going to shut down the rest of the tree. So it's going to shut down the worker supervisor, which in turn shuts down all the children, and it's going to restart the whole tree. And if if one of the workers keeps crashing, it's going to bubble up to the worker supervisor, and all the workers are going to be restarted, but the state will be left untouched, right? So in this case, nesting the supervisor is really it's a straightforward solution to this problem because it lets us compose the strategies, right? It doesn't limit us to 3 strategies that we have. It lets us compose the strategies in a more fitting way in this use case, right? Next tip is just supervise every process. This is a short one. Supervising processes means that you have more control over them, means that they are shut down properly, it means that they're traceable, so it's much easier to work with processes if they're all supervised. So my advice is generally don't spawn a process from another process, just try to spawn it inside, like under a supervisor somewhere. It's going to make the tracing easier, it's going to make the restart semantics and the crash semantics and the reliability easier to deal with. And then another super quick tip is just to name your supervisors. This is just from like experience in having production systems and going into the shell and saying, how do I find this process? Because nothing is named here, right? So just like if you name your supervisors, it's much easier to walk the supervision tree in the shell actually, and just say like, what are the children of this supervisor? And then you can usually get an idea of where you are in the supervision tree. It's much easier. And then the last thing I want to talk about is testing supervision trees. So this is a topic that is not really covered often. It's how to test supervision trees. My best advice is just test them as a monkey would do. Just like go shut down stuff and see what happens and make sure that nothing breaks. Observer is a really good tool for doing this because you can just really literally go in and you see the supervision tree and you can like right click on a process and say kill. And see what happens, right? And see if your application keeps running or if it cascades. So my recommendation is when you're building a supervision tree, just try to, go around and kill stuff and check that it works. It's manual, but it still works as a testing tool. If you want to have a more structured testing tool, this library exists from Fred Hebert called SUPS, and it's basically property-based testing applied to supervision trees. So it will programmatically go and shut down random parts of your supervision tree and make sure that your application is still functioning. If if it creates a failure or if it causes a failure, it's going to try to shrink it to a more manageable case where it does the usual property-based testing thing where it tries to create a minimal reproducing case of the failure, so it's really nice. It's a bunch of work to get it set up, and it's not for everyone. If you have a simple supervision tree, you probably don't need this. But if you have a complex supervision tree and you need to trust that it works, this can be a useful tool. Okay, so enough about supervisors. I want to talk about how your system interacts, how your processes, how the process lifecycle interact with external components of your system, because this is something that I think everyone should know how to do in Elixir. And the bulk of it is connection handling. So it's when you have a process that represents the connection to an external thing in your system, right? A very common use case is where you have something like a database. So if you have your application and you have a Redis connection process that is connected to a database. Connected means it has a TCP port open, right? And it could be Redis, it could be Postgres, it could be RabbitMQ, whatever. It's just connected to an external part of your system, right? So what I see often happening here, and what I see often discussed in Elixir and Erlang, in the Elixir and Erlang community, is what happens if the connection goes down, right? We have a connection between your Redis connection process and your Redis database. What happens if the connection goes down, right? Usually what happens is that the Redis connection process crashes. That's an intuitive thing to do, right? Because we're taught in Erlang that, we have supervisors, right? So it's just going to be restarted. The big problem is that supervisors do not have logic for proper restarting of stuff. They're just for emergencies, basically. They just do an emergency restart, right? They just bring the process back to life and not care about spamming Redis with connection attempts or anything like that, right? So often in these situations, you need more logic around reconnection, for example, right? For example, if Redis goes down in this case, you want to reconnect, but with timeouts, and you want to reconnect with like an exponential backoff where you try to reconnect after 1 second, 2 seconds, 4 seconds, and you don't want to just keep reconnecting because otherwise Redis might never be able to go back up, for example, because it's spammed with connection attempts, right? So the solution for this is to not use supervisors as restart, like as a controlled restart mechanism, just as an emergency restart mechanism. And the solution here is to make the Redis connection a connection process, a connection manager. So it should not be that tied to Redis. It should be a process that aims and not crashing ever, like every other process, right? Like it should be written so that a network failure, for example, is an expected condition, right? It doesn't bring the process down. It just means that if the network is down, the Redis connection will be in a disconnected state, and it will just answer to clients, to requests, saying, I'm not connected to Redis right now. And then it's the responsibility of the application to actually deal with that, with Redis being down, right? It's a semantic responsibility. Maybe if you're using Redis as a cache, you just hit the database when Redis is down, right? So the Redis connection here becomes a connection manager, and it doesn't go down. So, and if the connection goes down, it can actually have logic to retry, to try to reconnect after 1 second, 2 seconds, to have exponential backoff, to have all the logic that you want, to have proper logging of the connection going down, all the logic that you want when you're trying to reconnect, right? The deal, as I said, is just that like you make this process aware of when the connection is on and when it's off, and it just replies accordingly, right? So if it's connected, it's going to reply with OK and then a response when you make a request to Redis. Otherwise, it's going to return an error. And then the application decides what to do. Another important thing that this way of thinking unlocks is that you can have, when you're initializing your process, your Redis connection, you can do asynchronous startup. So when you're starting your supervision trees, usually if you have an external connection, you don't want to wait for that connection to be up in order to start, right? Because if you have, for example, if Redis is down when you deploy your application and your application starts, then you'll never be able to start your application until Redis is up, right? So the solution in those cases is to have an asynchronous initialization. So if you have a gen server, for example, you have init, that's what the supervisor waits for. When you have that, you can just basically set up the state and then do this continue connect thing. This is like a recent thing in Erlang, but it's basically saying, just start the process and then call this handle continue callback, telling it to connect. So it's going to basically the supervisor is going to start it, and then after that, the process is gonna try to connect to Redis, but the process will be alive and responsive there, right? And it's going to return. If you try to hit it as soon as it started, it's going to return an error, because it's not connected yet, probably, but your application should be able to deal with errors like that anyways, right? So might as well just do that. If you really, really need a process, you can actually do synchronous initialization, and you can erase if you get an error when the connection is disconnected. But in my experience, most applications fall into this category where you have a synchronous initialization of connections, and you have just error tuples usually. When something goes wrong, you don't really raise, you just handle them gracefully, right? Because they're super expected case. Like if the connections goes down all the time, and especially with like platforms as a service or like if you have hosted Redis, for example, they're going to shut it down and restart it just to update it. And I mean, this is going to handle it gracefully, right? A nice tool to deal with all this stuff is Gen State Machine. This is a recent-ish addition to Erlang. But it lets you build very nice state machine processes. And the state machine for a connection process is pretty simple. It's usually just a connected and a disconnected state. So you have a disconnected state where if you receive a request, you reply with an error. And then you have a connected state where if you receive a request, you actually reply with the response. And then you move between the states by just connecting and disconnecting from, when you disconnect, you go to the disconnected state. And when you connect, you go to the connected state. Funny thing is that I am able to do typos even when writing with my hand, not just with the computer. That's missing a C, you know? It's connected, not connected. Anyways, one thing that happens when you have these connection managers or disconnection processes is usually that they easily become bottleneck processes, because you don't want to have, in a system, for example, you rarely want to have a single connection to Redis, right? Because that's going to be slow. That's going to make it so that if that connection goes down, then no part of your system can talk to Redis. So that becomes a bottleneck, right? Either performance bottleneck or reliability bottleneck, but it becomes a bottleneck. And a common example that we always do is a cache. Like if you have a cache process that is gen server, and every other process has to send a call to it and get a response, in order to access the cache. Since the process is always sequential, right? So when you do that, you actually are doing the calls sequentially. So you're having all the calls are going through the cache, and the cache is becoming a bottleneck here, right? A common solution for this kind of stuff is something like ETS, so something that's accessible from everywhere. This is it's a common pattern to have an ETS protected table. That means that everyone can read from it, but only the owner can write. And this makes it really easy to not have race conditions for writing, because you can still have all the writes go through the cache process, but all the reads can happen actually in parallel from the ETS table without having to be serialized by a bottleneck process. When you can't use ETS and you still have to use, when you can't use something like ETS at least, and you still want to have better distribution of resources, you usually go to pools. So pools are a way to basically share resources and like have multiple instances of a resource. In the case of a connection, usually that's what you want, is you don't want a single connection to something like Redis, you want a bunch of them. So that's the idea behind pools. You have a resource and you have multiple connections that are connected to that resource, and then you choose a connection and you use that so that you can choose multiple connections from multiple processes and speed up and not have bottlenecks, right? There are two kinds of pools. This is a really, really common thing to write and to use in Erlang and Elixir. That's why I'm talking about it. But the main pools that I always see being used are checkout-based pools and name-based pools. So there are the two types. The checkout pools work by having a pool manager or a pool coordinator, I don't know what to call it, but basically you have a resource, you have your pool, and then you have something that manages the pool. You have your pool of connections, and then you have something that manages the pool. And when you need a connection, you ask the connection manager, can you give me a connection? And it's going to check it out of the pool, it's going to give it to you, and you're the only one that can use it. And then you can check it back into the pool, and you're good, right? And the connection manager just does basically the coordination of checking in and checking out connections from the pool. This works well, but sometimes it can still become a bottleneck, especially if you have very little logic in the pool manager. The pool manager can still become a bottleneck because every check-in and check-out request needs to go through the connection manager, right? In some cases, you can do name-based pools. So name-based pools are basically using a stateless registry where you look up connections. So a trick in Erlang and Elixir is to just name the connections, something like connection _1, _2, _3, and whatever, and then you choose an index at random when you want a connection. This is nice, especially because with the checkout-based connection, only one process can use your connection, but some types of connections are multiplexing, for example, right? So they can serve multiple clients at the same time to increase performance. And in those cases, this is a really nice thing because you're not checking out a connection, you're just basically getting the address or the PID in this case of the connection, and you're using that, and multiple processes can use the same connection. And we have one thing in Elixir now called registry. We had it for a bit now, but it's the same principle. It's a registry for names. So you can have a pool where the connections register on the registry with a name, and then the registry is basically an ETS table, so it's really fast to read and it's not sequential. You can do parallel reads. And when a client needs a connection, it just asks the registry for a connection, and the registry is going to give it a connection. And the nice thing is that you have semantics, like if a connection process goes down, it can deregister from the registry so that you don't get the process anymore. So it has really nice properties like that. Talking about all these processes crashing, so this is all I have to say about connections, but this is a central part of writing Elixir applications, in my experience, is that you usually have to write some persistent connection to something. So it's nice to have an idea of how to do that in Elixir and Erlang. Talking about errors and why all this stuff, when all this stuff goes down, I want to talk a little bit about error handling. So my advice is to you're working in a programming language that still needs to handle all expected errors, like all other programming languages. I think the let it crash motto is misused and abused because let it crash is like, it's a really nice semantic, because it means that in your application you can have crashes, and usually they're not going to bring down your system. That doesn't mean that you should rely on those crashes, right? It doesn't mean that you should just, if you have something that's, that's like if you have a disconnection from Redis, that's an expected use case. It's an expected error, right? It's not something that's just out of the blue. So if you crash on that, you're going to have a bad experience because it means that you're going to crash on a lot of other stuff, and supervisors are not built to just recover your system nicely. They're built to recover your system in emergencies, right? So my advice is to just crash on unexpected and unrecoverable errors, meaning that, for example, if you get input from the outside of your system and you validate it, if it's invalid, that's expected, so you just return an error to the user maybe. If it's valid and you validate it, and maybe, for example, you have a string that you turn to an integer, then you can treat that string, that integer, as an integer throughout the system. You don't need to keep validating that it's an integer every time, right? And then you can actually crash if it's not an integer, because then you're going into an unexpected state and really unrecoverable because you don't know what to do because you validated that, right? In those cases, it's fine to crash because you're going to, you're just throwing your hands in the air and saying, I don't know how to recover this. I don't know why this is happening. The best thing most of the time is to just crash in those cases because you're saying, I don't know what to do, and probably recovering this is going to cause more damage than just shutting down as soon as possible and restarting from a non-state, right? So my advice is to still handle unexpected errors, but be confident that Elixir and Erlang, if you build your system correctly with supervision trees and everything, they are going to take care of not bringing everything down, not burning everything to the ground if there's an error, right? That's a nice thing. So this is what I have to say about process and about a single node. I think I spend more time on this because I think it's more interesting than distributed Erlang. And I think that because this is what everyone that uses Erlang and Elixir has to deal with. If you don't, a lot of people that use Erlang and Elixir don't use distributed Erlang. So if you don't use distributed Erlang, you still have to take care of all this stuff inside a node, right? That's why I think it's interesting. But let's talk about the architecture of multiple nodes too. At the beginning, I mentioned that the nice thing, the thing that I like the most probably about Erlang and Elixir is that you have to have the same concerns that you have in distributed systems, even on a single node. So as we talked about this, you have to deal with asynchronous message passing, you have to deal with crashes in a single node. That stuff happens in a distributed environment with multiple nodes as well, right? The only thing more that happens is that you have unreliable message delivery. So in Erlang and Elixir, if you send a message from a process to another process on the same node, on the same virtual machine, the destination process is going to receive the message, period, at some point. You don't know when, but it's not going to get lost, right? That's a guarantee of the virtual machine. In a distributed system, you don't have the guarantee, right? Like if you send a message to from a node to another node, you have no idea if it got there unless the other node tells you, right? So that's the other concern that you have to have. That's what was in the superset of the concerns that you have to have when you're dealing with distributed system, right? The problem with the perception, I think, of Erlang and Elixir is that it's perceived as Beam solves distributed systems, which is very, very far from the truth. Beam really doesn't, right? This is my reaction. Does Beam? No. No. Beam solves distributed systems? No. Beam is just a good set of tools. It's a really good set of tools. But you still have to do all the work if you want to build a distributed system, right? It doesn't give you anything for free. It just gives you nice tools to deal with this stuff. And those nice tools are something like that. You have something like this. You have Send. Send is amazing because it works cross-node. And it has almost the same semantics, right? The semantics on a local node are just that your message is going to be delivered. You don't know when. You don't know if the other process is going to process it. You just asynchronous send. You're just sending into the void, but you know that it arrives. In a distributed environment where you have multiple nodes, a send is the same, but you don't know if it arrives. But it's nice because you still have to have acknowledgements in a single node anyways, probably, right? So you're going to treat it very similarly. And it's transparent. So this tool, you can just send messages across nodes transparently like you do in the same node. And since you build your system in an asynchronous and resilient way in a single node as well, this is going to be much easier to do. You have tools like Process Monitor and Node Monitor. They work across nodes. That's super nice. Like Process Monitor monitors the process inside a node. But if you monitor a process on another node, you can still get notified if the node goes down or if the process goes down. So it's super nice semantics. And since we do this a lot in a single node, it just translates very well to multiple nodes as well, right? You have tools like global process registration, where you can register processes across a cluster of nodes. That's super cool. That's a super good tool. But it's still like you still have to deal with stuff like network splits, right? So these are a really good set of tools, but not a solution, right? But to show how nice I think these tools are, I really like to show this example of this is code that you don't need to understand really, it's just for fun. But we have RabbitMQ, right? And RabbitMQ basically is a thing that has a bunch of consumers, and when it has a message, it delivers it to a consumer, and if the consumer acknowledges it, okay, otherwise it delivers it to another consumer. If the consumer dies, it delivers to another consumer. If the consumer disconnects, it delivers to another consumer, right? And we can build this logic, similar logic, well, pretty easily in Erlang. So we can use tools like Node Monitor. So you have a consumer, the consumer is sitting on a node, then you monitor the node. You monitor the PID as well, and you send the message to a consumer, and then you receive. You wait for the response. If the consumer acknowledges, good, the message is processed. If the consumer doesn't acknowledge and it goes down, you just give it to another consumer. If you have a node down, meaning that the node monitor kicked off and the node went down, you can just give it to another consumer. This code doesn't make any sense. Like, it's not implemented, it's not useful, but it shows that like you can use tools like monitor, node monitor and process monitor and message passing to really build something that like this works across nodes. That's incredible, right? You don't have to write any protocol, you don't have to write any HTTP or any TCP stuff, it just works. One thing that I like talking about is hot code upgrades. So who uses hot code upgrades? I don't even watch because nobody will raise their hand. First of all, like a big enemy of hot code upgrades, right? It's a very, very, very big enemy. You can't do it usually, right? It's really hard to do it with Docker. So, and a lot of people use Docker now. So what do you do with hot code upgrades? My question is, do you even need hot code upgrades? And my answer is probably not. The idea with hot code upgrades is that you have code that you can push to a running system without shutting down the system, and then the system upgrades the code without going down. So for example, in the modern world, this was useful when you had like telephone switches and you didn't want to cut calls because you deployed a new version. Like Erlang was running on a bunch of telephone switches and you didn't want to cut the calls if you push new code, right? And like the modern equivalent of that is kind of having something like WebSocket clients, right? Where you have a WebSocket client that is persistently connected and you want to deploy new code to the server. If you restart the server, you're going to lose all the WebSocket clients that are connected to it. So you could push hot code upgrades to the server so that the connection doesn't go down, right? The problem is that, have you ever had a phone? If you did, you know that connections are terrible. Like my phone loses connections to everything all the time, right? And my computer does too, even at home with the Wi-Fi. It's just like stuff gets lost, packets get lost. It's terrible, right? Internet is terrible. So like, what's the point of, I'm not losing my mic, perfect. So what's the point of like being so focused on not losing connections and not breaking connections if they're gonna break anyways? Like you're gonna have to have a really good way of dealing with these connections anyways. If you're building a WebSocket client, you're gonna have to deal with the server going down anyways. So like, does it really have a lot of value to have hot code upgrades? In some cases, but it's like we're, I don't know, 100 people, 70 people, so it's less than like, 1% because nobody raised their hand that they're using it. So it's a rare use case, I think, so just don't worry about it too much. But it's a cool thing if you're gonna try to sell Elixir, just say it has hot code upgrades, it's a cool feature. One question that I get asked a lot is like, do I use Beam or do I not use Beam for things, right? This is a really, really delicate question, I think, and there are camps for this, I think. Some people think that like the tools that Elixir and Erlang provide are awesome, and you should use them over other tools. And some people say just use Erlang and Elixir normally as you would other programming languages. I think that, so for example, if you need a database, do you use like a relational database, or do you want to use something like Riak, like a built-in Beam solution, right? Or if you want a key value store, do you want to use Redis, or do you want to use something like ETS Amnesia? I don't have really a preference. I think both are fine. Like I don't think something like Amnesia is a selling point of Erlang and Elixir. I think other things are selling points, especially because right now people are building complex multi-service systems with multiple technologies, and locking in to using something like Amnesia or using something like Riak means that you then have to use Erlang for everything, right? Having something like Redis or Postgres makes you more flexible on other things, right? So you gain things like interoperability, you gain things like, if you use Postgres, something like relational features, right? Like the proper, table relations. You gain data analysis usually if you use other tools, because there are tools that analyze the data you have in Redis, you have in Postgres, and it's really nice, and you don't have that with a bunch of Erlang tools. You have to build that yourself. Replication is super hard. Like if you have an ETS, just like try to build, like the first thing that everyone does is try to build a cache through ETS, right? Like it's hell, because like it works on one node, but when you have multiple nodes, like it's already a bunch of stuff that you have to deal with that you don't have to deal with if you have Redis, right? So it makes sense in a bunch of use cases, but I think not using those things makes sense anyways, and it's still worth using Elixir. That's my main point. Like it's still worth for the reliability, for the concurrency, for the way you reason about stuff when you write Elixir programs. It's still worth it even if you don't use these tools, right? The most important thing that I think you need to think about when you're dealing with this stuff, rather than focusing on the technology, on what tools you're using, is the communication between components of your system. That could be the communication between processes, could be the communication between nodes in your system, the communication between services. And by intercomponent communication really boils down to requests. Requests that go from one place to another, right? It can be requests from an HTTP connection process to a database connection process. That's a request. Like when you're saying, make this query on the database, issue this query on the database, a process is telling another process, it's asking another process to do something and waiting for a response. That's a request, right? It can be cross services in your system or cross nodes. Like you have an order service that makes a request to storage service. Those are all requests. And those are, I think, one of the most important things you have to deal with when you're building a system. And in Elixir and Erlang especially, because it applies to process-to-process communication as well. So I just want to touch on requests a little bit. And I think that there are three kinds of requests. At most once, at least once, and exactly once requests. And it's really important to know what kind of request you're making when you're making a request. It's between processes or between services or between nodes. It's important to know what kind of request you're making. An at most once request means just try to send the request. If it gets lost, like it just shouldn't happen more than once. But if it doesn't happen, you know how to deal with that, right? So it's kind of a black hole. This is the philosophy behind the at most once request, right? Like just try, and a good at most once request, for example, is a push notification. Like you want to send a push notification at most once, because if you miss it, the user usually doesn't notice. If you send it twice, they definitely notice, right? Because they have to. So this is a good use case for having at most once requests. In Erlang and Elixir, when you have inter-process communication, you never have at most once requests, because the message is going to be delivered to the other process, but you have guarantees on that, right? But for inter-node communication and inter-service communication, this is a really important type of request, and it's the cheapest one, because you just try to send it, and if it doesn't get there, good. But it at least doesn't get there twice. At least once means that you want to make sure that the request gets processed, but you're fine with it getting processed more than once. So this is a little bit more expensive, because you have to basically send the request, and then if you get an acknowledgement, you're good. Otherwise, you have to send it again. So you have to keep retrying until you manage to get the request. On the other side, so the retry is the important thing here to make this work. And this is important when you, for example, you want to I don't know, write a row on a Cassandra database where if you write it more than once, it's fine, but you really want to make sure that you write it. That's an at least once kind of request, right? And the key behind it is really idempotency. So idempotency means that if you apply the request or apply an operation multiple times, it's the same thing as applying it once. So that's the trick behind at least once, because you just do the same request again and again, and it's fine. So if you make your code so that handling the request is idempotent, then you can have at least once, right? Some cases require exactly once. That's really just super expensive, right? Because you have to make sure that you have to keep state on both the sender and the receiver. The sender needs to make sure that it retries. The receiver needs to have some state so that it doesn't process the same request twice. So for example, you have to have a request ID, and the receiver needs to keep store of request IDs and check every request so that it doesn't process it twice. So it's very expensive. This is useful for example, credit card transactions, right? Like when you want to transfer money between two accounts, that's an exactly once request. It has to happen, but it has to happen only once, right? But if you can avoid this, just avoid them because it's super expensive. So this is super important. Requests are, I think, like main thing you should focus on more than technology, more than anything. It's just like how does your system interact between inside the system and with other systems on the outside. In conclusion, just, I mean, it's an important quote: use the right tool for the job. So if you have, I don't know, if you have Redis already, just use Redis. For example, if you want to set it up, just use whatever fits. That's my advice. Keep in mind that systems today are complex. They are made of multiple things, so when you make your choices, I still think that Erlang and Elixir are an extremely good thing. We use it at work, and we use it like shoved in Docker without any distributed Erlang feature, and it's still amazing. Like we still get the reliability, we still get concurrency in each of the nodes, and it works very well. And it interacts with like Go services that we have, Python services that we have. It just works, right? But know that you have a bunch of tools on top of this, like ETS or Amnesia or React or whatever. You have a bunch of tools on top of this that you can take advantage of if you have an Elixir-only system. Then learn about distributed systems, because as I said, like Beam doesn't really solve distributed systems, and a lot of stuff today boils down to just distributed systems. So my advice is to learn about that. And my advice is to take the Beam architecture, the reliability, the concurrency, the supervisors, the request stuff that you have to think about, just bring it with whatever you're working on. Just like think about this stuff when you're writing Go or when you're writing Node or you're writing whatever, just think about this stuff. A bunch of resources. Designing for Scalability with Erlang.cp is one of my favorite books. The author is here, probably. And then we have from Francesco. Then we have Fred Herbert's blog, fred.ca. This is really like, just go read every article. It takes a while, but it's worth it. And Distributed System for Fun and Profit is a book if you want to learn more about distributed systems. And I'm done.
Thank you very much. We are a little bit over time, so if you have questions for Andrea, you can find him on the coffee break, and of course here. And again, thank you very much. And now switching to Spanish for a second.